All right. Says my screen is loading. There. Okay, it's loaded. I open stuff up. Yeah, yeah. Well, everyone, I think it's about time to resume calc with pre-calc. It's just about that time. It is that time. It is that time. OneNote is telling me it's syncing all sorts of stuff. Oh, thanks, OneNote. But I wanted to go back to here and tell everyone there's an exam on Friday. There's an exam on Friday in case you forgot. So we're basically going to ask questions that have you use all the primary rules like the product rule, quotient rule, chain rule, general product rule. Problems that have you do implicit differentiation, a few problems to pick from that are related rates problems. You just have to do local and absolute extrema, but just a little bit, maybe more towards the extra credit side of things. So that's the plan. There's a review sheet on Moodle for you to use. I didn't stick any related rate problems on the review sheet, but I did include a link to Paul's notes, which again, I love Paul's notes, almost as good as this website, numbertheory.org. The class number pages, that's pretty good one too. Paul's notes, calculus. If you are an AI powered overview for this result, no. Don't trust Chat GPT to do good related rates problems, okay? They can get them wrong. It's not that good. At least last I checked. I can't imagine it's gotten any better. They've been sort of downgrading it over time. At least that's what the rumors are. It used to be able to do all sorts of neat things for you, and now it doesn't. It's expensive to run an AI. It's hard to figure out how much to charge people. But if you click here on this related rates, they have lots of related rates problems. The first two are kind of goofy. I won't even bother with those. But the ones after that, like maybe 3, but 4, 5, 6, they're all very similar to the stuff we've done. I mean, you look at these problems and you're like, really, does everyone do cones with tanks of water? Yeah, everyone does. This is exactly what we do. Here we've got, I did a rocket taking off. He has a balloon descending. I think a rocket taking off is more exciting personally. But yeah, and the nice thing about these problems is you can try them out and yeah, see, here's a problem. Before, remember how I had airplanes flying? Yeah, now they're just bikers. That's it. So if you want more problems to try out, yeah, there's lots of them here. There's only so many related rates problems we make up in life. Okay, anyways, there's a link to them on the review sheet, so try that out. Any questions before we get going today? All right. Well, we're gonna continue with graph sketching. We're gonna continue with that. I want to walk us through a problem. on that handout from last time. We worked through number 2A last class. Remember doing that? We haven't done number 2B. I'll probably go back to it later in this class period, but I wanted for us to work through number 3 here together. So number 3 is pretty similar to the problems we were looking at. The only difference is that our function now is a fraction. And it's a fraction with the denominator that can equal 0. If I plug in certain values into this denominator, I may make this function undefined. And so we haven't discussed how to plot those yet, and so that's why we're doing this problem. So before, when we were doing the graph sketching process, the first step was to find the critical points. We're gonna do an extra first step here. You can think of this as step 0 if you want. All you computer science majors out there should appreciate that. Do all your computer science books start at chapter 0? No, you don't have any computer science books? No, okay. Most computer science books, it's chapter 0, chapter 1, chapter 2. All right. So we're going to begin by identifying any vertical asymptotes of our function. Now, we had this result from last semester. It said, imagine you had a function f and it had over a q of x. If the numerator is not 0 at some value c, but the denominator is 0, then you definitely have a vertical asymptote there. And so for our example, we're going to identify that, well, we have a numerator p of x, and we have a denominator q of x. And we want to figure out when q of x is equal to 0. When is q of x equal to 0? And so I'm going to set x squared minus 1 equal to 0. And does anyone know when is that denominator equal to 0? 1 and negative 1, right? X is equal to negative 1 and 1. And then we'll check that p of x is not 0 at these points. And so if I plug negative 1 into this numerator expression here, I'll get 5 times negative 1 squared, which is 5. And I have it on good authority that 5 is not equal to 0. Similarly, I can plug 1 into p. 5, 1 squared, I get 5. And 5 is not 0. So thus, since we've checked that the denominator is 0 at both of those points, and the numerator is not, we have vertical asymptotes at negative 1 and 1. All right, that's just a good first check we ought to do whenever we have a function that is, a little complicated, such as this one. Now, the next step, of course, normally it's the easy step, right? Find the critical points. Well, it gets a little bit trickier when your function is a quotient, because now we have to use the quotient rule, right? So let's use the quotient rule together. F prime of x is going to be low, which is x squared minus 1 times the derivative of the numerator. That'll give me a 10x minus high, derivative of low, 2x, all over x squared minus 1 squared. And so I was able to take the derivative, and what I need to do next is find when the derivative is 0 or when the derivative is undefined. Now, to find when the derivative is 0, I unfortunately need to simplify my numerator. So this is where doing algebra right really matters. I'm going to take x squared minus 1, and I'm going to distribute this 10x across. So I will get a 10x cubed minus 10x. Meanwhile, here, I'll have a minus 5x squared times 2x. That'll be a minus 10x cubed here. And when you look at it, it's not that bad, is it? Something special happens. All right, you get the 10x cubes to cancel each other out. And so stop being, what are you doing, OneNote? All right, there we go. So in the end, our function is just negative 10x over x squared minus 1 squared. All right, so now the question is, when is this derivative equal to 0? Does anyone see when it's equal to 0? 0, right? That numerator is 0 when x is 0. So we've got a critical point at x equals 0. Are there any points where it's undefined? 1 and -1 again, yeah. So our critical points, maybe I'll write them in this order, are -1, 0, and 1. So there we have it. Those are our critical points. Now let's figure out where this function is monotonic, which is fancy talk for when is it increasing. And so we're going to have some intervals here. We'll go -infinity to -1, -1 to 0, 0 to 1, and 1 to infinity. And I'll throw in some test values here. We're going to plug them into this function right there. What's a good test value you think you should plug into this? -2 looks good to me, yeah. Now, if you're a real whiz at math, right, you should be able to do this computation in your head. I'm going to try doing that right now. Of course, you can use your calculator as well. But -10 times -2 gives me positive 20. This will be a 4 minus 3, which will be a 3 squared. I just get 20 over 9. I did it right. And I'm not sure what that number is exactly in decimal form. Well, I guess I could probably figure it out, but it's 2.2222222. But I'll just leave it at that. All right, that looks good. 20 over 9. Did I do that right? I think so. All right, what's a good test value here? -1/2 or -0.5. I will try doing my amazing arithmetic skills here. They're not that amazing. I should get a 5 in the numerator. In the denominator, I get 3/4 squared, which is 9 over 4. So I'll get a, do I really get that? I think I get 20 over 9 again. No, it's negative. Yeah, I get 20 over 9 yet again. All right, this is worth checking. Am I right? Yeah, this is, you know, the kids say this is sus. All right, I'll plug in our derivative here. No sense trying to, you know, demonstrate our arithmetical superiority. We can just try that, right? So at first I did p of -2 and I said it was 2.2222. Okay. That's the same as 20 over 9. And now I'm saying I should get the same answer with the, oh boy, I screwed up there, huh? 8.8888. Where did I screw up there? So I get a 5 there, right? I get a 5. And it'd be a 5 over, oh, it'd be 5 times 16. 5 times 16, yeah. 5 times 16 is a big number. That's 80. Yeah, 80 over 9. All right, okay, that was sus. I got positive when I plugged in the -1/2 there. Now when I plug in 1/2, I'm pretty sure I'll get an 80 over 9 again, but this time it'll be a -80 over 9. And when I plug in for +2, I should get a negative 20 over 9, which is again negative. All right, so and so now I'll have sort of the categorization of whether it's increasing or decreasing. And so I have decreasing, increasing, decreasing, decreasing. There we go. Okay, we found the intervals of monotonicity. All right, now we got to figure out where there are any local extrema. Does anyone see? Well, first of all, we have 3 critical points. Can there be a local max or local min at -1? At first, you may say, yeah, you could always have one of those at a critical point, but not in this case, because there are vertical asymptotes there. So although these are critical points, we needn't worry about them when finding the local extrema. Really, the only critical point we're interested in is 0. And what sort of thing do we have there? It is a local max at x equals 0. And of course, it behooves me to plug 0 back into my original function to see what f of 0 is. I'll get 0. Thus, local max at the origin, 0, 0. That's convenient. All right, that's it. So we identified our local extreme. Well, I guess technically this is in the wrong spot. I should have it in part D, but anyways, it's not a big deal. All right, next up, I need to find my second order critical points, which means I now have the distinct privilege of differentiating that piece of work. Oh, no, that's not going to be fun, but we can do it, folks. I believe in us. We can do it. So this is f prime of x, and now I just need to do the quotient rule yet again. This one I definitely did not give enough room. All right, so low. So I take that x squared minus 1 squared with the whole thing times the derivative of high. So the derivative of negative 10x is negative 10 minus high. I didn't realize your feet went that far. Okay. Yeah, you gotta stretch out a little bit from time to time. Minus high. And then I have to take the derivative of, well, x squared minus 1 squared, but that looks too, so I'm gonna write this and say, promise to the future, take the derivative of that. All over an x squared minus 1 squared squared. There, easy peasy lemon squeezy. All right, now, having done that, let's figure out what would the derivative of this x, what is this thing here? What is the derivative of x squared minus 1 squared?
X squared.
To the 2x? No, it times 2x, yes. Right, we're using the general power rule here, which if you haven't memorized this, it may be time to consider getting a tattoo. It is n g of x to the n minus 1 times g prime of x. One of these days I'm going to get in trouble. Some parent's going to call me and say, you won't believe what my son got on his arm. Oh boy. Yeah, that might happen someday. All right. So, okay, I'm going to be a little lazy now. Replace this derivative here with that thing Eaton just told us the answer to. So honestly, that would be the best parent complaint ever. I mean, unless you did like something kind of stupidly, it's like SpongeBob with a speech bubble, and then there's the general power rule. That would be extremely tasteful. All right, now, I don't know if you remember this, but there is this kind of technical simplification I can do here at this point. Does, does anyone know what that technical simplification is? I can pull out one copy of x squared minus 1. So I've got one copy here, and I technically have two copies there. But I'm just going to pull out one because I've got two separate terms. Remember this? Term 1, term 2. And I've got a copy of that in both of them. And so, okay, this is where things get fun. I'm going to pull that out. I'll have an x squared minus 1 all pulled out there, and then I'll be left with an x squared minus 1 times negative 10 minus a negative 10x times 2 times 2x. And what I've done is I've kept one additional copy of x squared minus 1 present in term 1, because yep, there's two of them. I can only pull one out. As for term 2, I can pull out this x squared minus 1, and I'm just left with, there's nothing there left of x squared minus 1s. And the denominator, how can I rewrite that? To the fourth. And now we can do a little bit of more canceling. What we can do at this point is, because we've factored this x squared minus 1 out of the numerator, I can cancel one copy of the x squared minus 1 here with an x squared minus 1 there. And when I do that, I'm going to get just that part in square brackets. There we go. How do you like that? I mean, I guess you don't have to like it. You just have to do it. Okay. So that is the second derivative. We haven't even found the second order critical points yet. We're just doing a derivative here. I'm gonna scooch this over to the right. Lately the lasso tool has been acting all glitchy on OneNote. I don't know if it's designed that way on purpose. Look at that. See how clunky it is? It just doesn't have the same pep it used to have. All right, so what I can do next is distribute everything. In the numerator, I'll get a negative 10x and a plus 10 here. So negative 1 times negative 10 gives plus 10. And then here, I have a minus and a negative. And so the minus and the negative cancel out. I'll just have a plus. And then all this is multiplied together in one big mess. So I'll have 10 times 2 times 2. That'll give me 40. And then I have two copies of x. That'll give me 40x squared. All over x squared minus 1 cubed. And does anyone see what magical thing we can do with the numerator? Oh, did I do something wrong? Oh, did I miss oh, it is supposed to be negative 10x squared. Keynes, I forgot the square. Well, okay, that means we could simplify some more, right? We now have a 30x squared plus 10. I should double check this, okay? I got answers that I have worked out in the past that are guaranteed accurate. Because past Brandon is a little bit more reliable than present Brandon, just a little bit. Oh dear. Past Brandon's saying I shouldn't have this at all. We got to go back and check all our work. Oh no, I'm looking at the wrong thing. Oh, phew. I was like, this answer isn't even close to right. Okay, let me take a look. Yeah, this is right. Okay. Phew. Phew, we did it. All right. One last thing I could do is I can factor a 10 out of all this. This will give me a 3x squared plus 1 over this x squared minus 1 cubed. All right, there we go. All right, now the question becomes, when is that thing equal to 0? Can you think of any values that you plug into the numerator and out pops a 0? I mean, I guess we could try it. We'll solve for numerator equal to 0. 3x squared plus 1, if that's equal to 0, then 3x squared is equal to -1. And that means x squared is equal to -1/3. And what does that mean my x is equal to? Plus or minus square root of -1/3. Oh yeah, so I guess right there, that's where the critical points are, right? Oh, it's undefined. Yeah, this is bad. Yeah, bad. Bad. Right. We don't take square roots of negative numbers in this class. If you try to take a square root of a negative number, like you hop over to Desmos and you're like, what is square root of -1/3? It just says, that beats me. One of the drawbacks of Desmos is it doesn't let you do complex numbers, but that's kind of intentional. All right, so that means the numerator is never 0. So there are no second order critical points from that. Is the denominator ever 0? 1 and -1. So we still have 2 second order critical points. We have second order critical points still at -1 and 1. There we go. Yeah, maybe I didn't give you enough space for all that, did I? Maybe you can make it fit. I don't know. I try to write more than is needed, just, so you can conceivably follow it. All right. Now, just because this is the case doesn't mean, none of these second order critical points resulted in the second derivative being 0, but we still have to do these intervals of concavity. So let's do it. Now our second order critical points are -1 and +1, so I should get the following intervals. And now I have to plug in some test values into this. So I'm going to kind of go back and recall for myself what my second derivative is. The second derivative, which I just lovingly computed earlier, is this piece of work. Well, look at that, huh? All right. All right, what's a good test value? -2. Can I actually compute that in my head? I'm not even going to try. Okay, let's just enter it in on Desmos. All right, I'll get rid of this undefined thing. Q of x is equal to, what was it? It was a 10, 3x squared plus 1, all of that over x squared minus 1 cubed, I think. Yeah, that was it. And so I'll do Q of -2. I get 4.81. All right. What's the second derivative at 0, you ask? It's not 0, it's gonna be 10. Just 10. No, it'll be -10. -10. Here, let's let the computer do the work for us. Yeah, -10. Okay, now you believe it. Now if I plug in 2, I imagine I'll get 4.81 again. I do. And so now if I want to look at the concavity, I can see that it's up, down, and then up. There we go. This is a long problem, isn't it, huh? All right, up, down, up. That's the concavity. All right, are there any points of inflection? Any points where the concavity change? Yeah, looks like at -1 and 1. The concavity does change there, but those are not points of inflection. No points, no inflection points. Does anyone know why -1 and 1 don't work? Yes. Because x equals -1 and 1 give vertical asymptotes. So that's why it's the first step, because otherwise you're wasting a lot of time trying to evaluate your critical points and your local extrema, and they're just a bunch of vertical asymptotes. All right, let's go back to the original function. What was the original function? The original, oh boy, look at this. Do you remember all this fun stuff? This was fun, yeah. Yeah, fun, lots of fun. All right, so our original function, just so we have it here, was 5x squared. Was it 5x squared over x squared minus 1? That's what it seems like. So we have this function 5x squared over x squared minus 1. And what we want to do is we want to figure out what happens when x goes to infinity. So we want to figure out, say, what the limit is as x goes to infinity of this thing. And I don't know if you remember this. Maybe you can recover it through hypnotic regression, something. But we did do this. We went over how to compute such limits. And I have two theorems here, but the one you really want to look at is theorem 2. Theorem 2 basically says, look at your numerator term and find the term with highest degree. That's what we call xn. And so in our numerator, there's just one term, so that makes it the highest degree. And then look at its coefficient. That's what we call an, and the coefficient here for us is 5. And then you can play the same game here. You can say, all right, what's my largest power of x in the denominator? In our case, it'll be x squared. And then you can ask, all right, well, what's the numerator? What's the coefficient? And what's our coefficient here of x squared? Yeah, it's an implied 1. I'll just kind of write off to the side there. And so the idea is you're going to take this an over this pink bm, and you're going to compute a limit. Well, I guess I'm supposed to have that 5/1 in front, right? And it says the limit is going to be the limit as x goes to infinity of x to the n minus m. Now, what's my n in this case? 2. All right, you see how that matches up? X to the n x squared, and my m is also 2. And so in the end, it's just going to be 5 times the limit as x goes to infinity of, well, x to the 0. And what does x to the 0 equal? 1. And so in this case, our limit is just going to be 5. And basically the exact same process. I'm not going to write it all out. You're welcome to. We'll show that 5x, if we go to negative infinity, we're going to get 5 as well. This is important because this tells us where our horizontal asymptotes are. So normally in the prior problems we did, when we took a limit as x goes to infinity or negative infinity, right? That would indicate that usually the result would be positive infinity or negative infinity. We draw these curves that increase upward, but we do not have that here. And so we can conclude, thus there is a horizontal asymptote. Asymptote at y equals 5. There we go. So we're able to generate a lot of information here about our function. We're able to figure out where it's concave up, concave down, where it's increasing, decreasing, where the vertical asymptotes are, where the horizontal asymptotes are. We now have enough information to be able to plot this. So we got a lot to do. We've got to plot vertical asymptotes, horizontal asymptotes, local extrema, inflection points, all the things. So I'm going to begin by just doing the vertical asymptotes. I like to do those in gray. I think gray is a great color for asymptotes. There we go. So does anyone remember where the vertical asymptotes are? 1 and -1. So I like to do a nice little dashed line here. It'd be nice if OneNote could just do a dashed line for me. Wouldn't that be nice, OneNote? If it wasn't for this class notebook feature, I'd probably use another app called Journal++. And it's really good because you can draw a line and you can make it dashed. Beautiful. But it doesn't have like the class notebook features. I don't know though. Maybe I'll suggest, maybe I'll offer to program it. That would be good. All right, so there's my vertical asymptote. Where's our horizontal asymptote? Does anyone remember that? 5. So 5 is right here, so I'm going to draw some more dashed lines. Basically, I know my functions are going to have to hug up against these asymptotes somehow. May not be exactly clear on the details yet, but I'll figure it out eventually. All right, I believe we had a local max, right? The local max was at the origin. So this was, I'm just going to write that this is the local max. And it would also be good to know where this function is concave up and concave down. So let me grab that information from here. Sometimes you just can't like paste things where you want. You know, OneNote's just like, I don't know about that. I don't know if I can just paste it where you want or guess where you wanted it pasted, even though you scrolled all the way down there. Perhaps you wanted it at the very top of the screen, or maybe you wanted it at the very top or bottom. Who knows? That's how OneNote thinks. Okay. So I had a little color code system, right? I believe I used orange for concave down and green for concave up. You don't have to use the same colors as me, but I'll try to do it here. So I have that this is concave down here. So I'll just kind of highlight that there and then concave up elsewhere, concave up here and concave up here. There we go. All right, so that's helpful. You know, I'm also going to grab where it's increasing, decreasing, just so we can check it to make sure we're doing it right. So where's that increasing, decreasing data? Here it is. Grab that. Scroll down here. Tap here so that OneNote knows I want it somewhat nearby. I don't want all this test values though. Here else. Yeah, there we go. There we go. Things are a little off center there, but I think it still makes sense. Okay. So where do we plot first? Well, we're so used to moving from left to right that sometimes that can get us hung up. It's actually a little bit easier if we simply start at the local max here. Local maxes have pretty obvious shapes, right? And we're going to have this sort of shape, and that's good because this is a concave down shape. Now we know that there are vertical asymptotes here at 1 and -1. And because of that, this curve is going to have to hug up against it as it goes down. And so that vertical asymptote information, that was pretty important. All right, as for the rest of it, it's like, goodness, what do you do? It's got to be concave up, right? Concave up. Let's think a little bit about this interval here. We'll call it the pink interval. we need it to be concave up and increasing, right? So if I draw just sort of on the side here, a concave up shape, I can see that really the only shape I need is this increasing part. So I want that increasing part. And I also need whatever curve I draw to have 5 here as a horizontal asymptote, and this vertical and -1 here as a vertical asymptote. Now, if I were misguided, maybe I would be like, well, maybe I can like draw it here somehow. No, no, that would be bad because now it's not concave up here. It's starting to go concave down. So where do you think I should put this concave up increasing shape? Maybe here, maybe here. Yeah, this top left corner, that's a good spot. We're gonna want maybe a function like that. Do you see how that is a concave up shape? It is increasing and it is approaching both asymptotes appropriately. That's good. The other interval of interest to us will be this 1 to infinity one. And that one will be concave up and decreasing. It'll be a reflection of it, yeah. That's tricky, huh? But go ahead, you can plot it. It has roughly that shape. This is very accurate. So that's how we plot things with asymptotes, and it only took us 40 minutes. So, with that exciting bit done, why don't you try out number 4, which is a lot easier, okay? I think you get number 4A. Try out number 4A. See if you can find all those things, the vertical asymptotes, the critical points. We can do it, everyone. Yeah, Lee has it figured out. You need a buddy on this one. It's like mountain climbing. You can try doing it by yourself, but when you make a mistake, the results aren't as good. By the way, too many people did not write sentences defining variables, okay? On this last homework. It was right there on the front of the problem set, but not many people actually did it. So people got whacked. But hopefully you'll remember now. Gosh. Jack is missing. I'll have to get Jack here again. So, and just a reminder, related rates is indeed a difficult topic. Do not be too disheartened, but do strive to understand it as best you can. Did anyone find any vertical asymptotes? Two, that's it, yep. Next up, find the critical points. Which means using the quotient rule. If I recall correctly, there's something kind of weird about this problem. There's a reason why it's doable quickly. Got some quirks to it. Yeah, it does. If you're scratching your head a little about your answer for the critical points, worry not, you're doing it correct. Maybe. Ah, I no, you're not being too loud. They're just very, very quiet in here. How's it going? Yeah, yeah, that's it. That's it. There's just one. Yeah, it's very weird, isn't it? Liz, you want to check anything? Yeah, you did it right. You did it right. Yeah. So if you take the first derivative, you will get the bizarro answer, -5 over x minus 2 squared. And so what are my critical points? 2, that's it. And it's also happens to only, it's a vertical asymptote too. So I'm gonna have no local maxes or local mins. It's kind of weird. How's it going, Zach? Good, okay. Well, that's a weird function. If you found it's decreasing everywhere, you're correct. These types of functions actually have a very special name. They're called linear fractional transformations. They're also sometimes called Möbius transformations. Or sometimes people pronounce his name Mobius in America. Heard of a Mobius strip. Same guy. Oh boy, this one's gonna be complicated. We gotta do that weird trick. Oh, actually, the real trick is really easy. How's it going, Megan? Yeah, yeah, that works too. Yeah, I'll still be roughly correct there. Decreasing regardless of the test point. So I'm working out the second derivative here. And it's really nice because f prime is -5 over x minus 2 squared. When I do the quotient rule, I'll have the denominator x minus 2 squared there times the derivative of this constant, which is always 0. So this whole term just drops away. Minus the numerator -5 times the derivative of the denominator. And the derivative of the denominator is 2 times x minus 2 times the derivative of x minus 2, which is, well, 1, so I didn't write anything down. And so you get 10 over x minus 2 cubed. So second order critical point at x equals 2 again. Now I plug into the second derivative. Yeah, -10 there for 1. When I plug in 3, I'll get a +10. So the concavity does flip. Goes from down to up. But because there is a vertical asymptote at x equals 2, I don't have an inflection point. All right, what's the next terrible thing we must do? we gotta do this. We gotta take the limit as x goes to infinity of our function. X plus 3 over x minus 2.
We have to take the positive and negative infinities separately. Or do you-
You could do them together, but I'm doing them separately just for. Sometimes you have to do them separately, sometimes you don't. In this case, you don't. Yeah, so how would I compute this? I would again look at those leading coefficients. They both have leading highest powers of x. They're both just x. Over as x goes to infinity of x to the 1 minus 1. Yeah, it all just equals 1. And the same is true if you take x to negative infinity. It's also 1. So we now have a horizontal asymptote at y equals 1. All right, that's all the raw information we need in theory to plot this thing. So I'm going to plot the asymptotes. I'm going to plot the intervals of concavity, and then I will leave it to you to, and I'll check to see if you're able to plot it correctly. It's one thing to be given all the information that you need to plot it. It's the other thing to, actually plot it. Like it seems like it should be easy to do, right? Like, oh, if I have all the information, it's just straightforward to draw the curve. Not always. And so the other one is that I have a horizontal asymptote here at 1, right? And I believe it is concave up. No, which one? Which way? Yeah, it is concave up here. It didn't straighten out for me. Concave down there. And it's decreasing everywhere, right? Decreasing everywhere. I'll let you ponder. How do you plot that? Any idea, Keaton? Oh yeah, okay. I'll give you the hint I did last time. So last time, like let's say I want to do the concave down shape, right? I just drew a little concave down shape. And I was like, okay, how do I make oh, did I get this backwards? I think I did. Yeah. Oh boy, yeah. That's why Keaton is stuck. And everyone else. All right, this is concave down. Oh man. Down. Okay. This is concave up. Okay. I trust there's some sort of pedagogical value to that mistake. I hope there is. Can I scooch this thing up a little, just a little bit? Just right there. Oh yeah. Up. All right, so I need concave down and decreasing somewhere on this orange portion. See if you can find concave down and decreasing on there. Yeah, you guys got it. Yeah, so decreasing and concave down is gonna look like that side, right? That's down. So I need that sort of general shape over here, and I need it to hug my asymptotes. And so if you came up with a curve like that, that would be roughly correct. And here I need concave up and decreasing, right? So that's going to have this shape here. And yeah, that's roughly what it looks like. This isn't exactly precise, but you can now sort of see what these shapes look like. How much time do I have? I have 5 minutes. Oh, that's not very long. All right, let's go back to number 2B. I kind of skipped over that one. This one, we don't need to worry about a lot of the complexities that are present in the other problems. You never have to asymptote anything because there's no, it's a bounded interval from 0 to 2 pi. So that's nice. So for this problem, we simply have to figure out our critical points to begin with, which means we have to take the derivative. So what's the derivative of this? Well, the derivative of x over 2 is 1/2. What's the derivative of sine? Cosine, right? And so I want to find the critical points. Those are going to be points where this derivative is equal to 0. And that's the same as finding the points where cosine of x is equal to 1/2. And how do I find those points? I got to get my unit circle up. Yeah. Let's pull it up here. Unit circle. I Google it every time. Here we go. They're all pixely. I think this one looks best though. Is it gonna load it? Yeah, oh, over here it loads it. Okay. Yeah, come on, zoom in there. Okay. Can anyone find the angle? Remember, cosine is which coordinate? The x or the y? X. So what angles give cosine of 1/2? Pi over 3 and 5 pi over 3. And that's it. So x equals pi over 3 and 5 pi over 3. So I guess I'll write it's not letting me erase these days. Come on. I'm wiggling my eraser all over the place. Okay, yeah. So critical points are at those. All right, I should make a little table here. In this table, because my intervals from 0 to 2 pi, my first interval will be 0 to pi over 3 here with 0 included. And then I'll have pi over 3 to 5 pi over 3. And then I'll have 5 pi over 3 to 2 pi. And as before, I got to figure out some test values, and you can just plug in whatever you would want to plug into this. I mean, I have my own preferences, right? So I'm gonna enter in this function into Desmos, 1/2 minus cosine x. So I can evaluate it easily. I'll call it p of x minus cosine x. And that's what it looks like right there. My test value I'm going to plug in is going to be pi over 6 because I think that's right in the middle, right between 0 and pi over 3. So I'll do pi over 6 here. I'll get negative 0.366. 0.366. What's a good test value to plug into here? Pi over 3 and 5 pi over 3. There's a lot of them. Pi is a good one, yes. 1.5. And then for this one, I need to be past 5 pi over 3. So I can try, say, for instance, 11 pi over 6. Maybe that's not as obvious an answer. At this point, you may just want to try decimals if it's not obvious what to plug in. But I'll do 11 pi over 6. Yeah, negative 0.366. So, okay, that tells us something. It tells us our function is decreasing, then increasing, then decreasing. But I'm out of time. That's it. All right. Well, we'll pick up, we'll have an exam on Friday. So that's that. Online students, any questions? I can't see any head shakes right now.
Corrections on that homework.
I think you lost a quarter point, right?
Yeah.
You can correct it. Go for it. But I'm not going to give any points back. You're fine. You'll make it in the long run, I'm sure. Okay. It was just an itty bitty mistake. Just an itty bitty. I didn't get perfect scores on homework, so don't feel bad. All right. Any other questions? All right. Okay. I'll see you on Friday. Bye.